Following up on our activity with seismic waves, we're going to talk about how seismic waves are used to explore Earth's interior. Now, just as a reminder to get all on the same page with terminology, an earthquake happens somewhere below the surface, and the place that the earthquake happens is called the focus. Just above it on the Earth's surface is the epicenter. Waves, of course, emanate from the focus, and they move in all directions. Now, a wave moving through something solid will move at a speed that is a function of the density of the material that it's moving through. So geophysicists can exploit this property of waves to learn something about the Earth's interior by measuring earthquake waves. By the way, geophysicists also create their own waves traveling through the Earth and use those to explore the Earth's interior, like this diagram shows. In this case, they're using a vibrator to pound the ground and send waves down, and those waves will reflect off of surfaces underneath and back up, and their travel time is measured. And that tells you something about the surface layers of the Earth, what lies at reasonable distances below. And this is used for exploration all the time. We'll talk about that a little bit later. Meanwhile, let's get back to earthquakes. A seismograph measures seismic activity. It measures the shaking of the ground caused by almost anything, but in this case we're talking about earthquakes. And in this case the time starts at the left and moves to the right, and at first we just have background wiggles, and then an earthquake wave arrives. And the first wave to arrive is called a P wave. It's a compressional wave, and it moves pretty quickly through solid medium. Then there is a secondary wave called an S wave, and that one is a shearing wave, and it moves at a reasonable speed also through a solid medium. And then finally, surface waves will arrive, and the surface waves are the slowest to get there, and as the name implies, they move along the surface. Surface waves are really important for earthquake damage. They tend to cause a lot of ground shaking and can be the primary cause of damage to buildings. P and S waves tell us something about the interior of the Earth. So let's look at both of them a little bit more closely. P waves are compressional waves, and if you are wanting to imagine yourself as a small bit of rock, as the P wave passes, that little bit of rock is squeezed and then it's stretched. And a slinky is a really nice example of this. If you pull and release a slinky from one end while the other is held in place, you'll see the individual metal bands move closer together and farther apart as the wave passes. And that's exactly what happens in a rock. There is compression and there is dilation, and individual particles move forward and backward, squeezing and stretching as the wave passes. This is another diagram showing the same thing. The direction of propagation is along the length of the block, and the individual particles also move parallel to the length of the block, squeezing and stretching with the material around them. Now, as you might imagine, if wave propagation requires being able to push against and stretch out from the little bit of rock next to you, then the more dense the material, the faster this is going to be able to happen. If the pieces of rock were quite spread apart, it would move pretty slowly, but when they're crushed closely together, the wave can move pretty quickly. An S wave is a shearing wave, and the motion is perpendicular to the direction of propagation. So in this case, the direction of propagation is still along the length of the block, but the individual particles are moving up and down. So seismic velocity varies with depth, and you've seen this diagram before as part of your exercise. Let's look at it again a little more closely and notice a couple of things. Within the mantle, both the S wave and the P wave velocity increases with depth, and that's because both of them increase with density. And so you can see that quite clearly in the mantle. But look a little bit closer at the top. There are two transitions where the velocity changes abruptly at 410 kilometers depth and 660 kilometers depth. And this is where the composition in the upper mantle is changing, and that causes the density to increase suddenly rather than gradually, as increasing pressure would do. There are, of course, other transitions at the outer core and again at the inner core, where you go from a solid to a liquid, and therefore the S wave velocity drops to zero, and the P wave velocity slows considerably from the solid mantle to the liquid outer core. Now, remember from physics that waves will both refract, which means they'll bend, and they will reflect when they encounter changes in density or boundaries in a system. And of course, they do this within the Earth, and we're going to take a look at exactly how to see what pathways earthquakes waves travel. So in this case, we're looking at an earthquake at the little star, somewhat below the surface. And if you look on the right-hand side of the diagram, this diagram shows the primary P waves and S waves, and they're very simple patterns. In this case, they're showing you two waves that have gone down and have then bended back towards the surface and are registered at a seismic station at the end of the arrows. And of course, the surface waves are shown on this side too. These are the simplest wave paths that there are, but there are many other waves that happen. And on the left-hand side, it's showing you some of the other more complicated wave paths. For example, the very first one is a PP wave. This one, from the earthquake, the wave emanated up towards the surface, bounced off the surface, went back down again, and then emerged at the location of the PP. So it was a P wave the whole way. There's also an S wave shown there. But let's take a look at some of these ones that get down to the core. This wave traveled down, bounced off the core, reflected off the core, and came back up to the surface, and we call that one a PCP wave with a lowercase p because it was a P wave, compressional wave, in both of its pathways. That wave could also have hit the core and refracted and traveled through the core to the other side, and then refracted again. The density changes abruptly and come back up to the surface way over here, and we call that a PKP, the K meaning it traveled through the core. So scientists use these designations to look at a seismograph recording of an earthquake and tell what its pathway was. Let's talk about why these paths curve. You might remember from physics class Snell's law, which says that as a wave passes from one material to another, it will refract, and that angle of refraction is a function of the difference in density between the two materials. When the wave is traveling from material 1 to a more dense material 2, then the refraction is away from the perpendicular, like it's shown here. And of course, this is how the Earth works. The layers are more dense as you go deeper, and so the refraction is always towards a shallower angle as you move towards more dense materials in the Earth. Now, as you go through layer upon layer upon layer, or even just gradual change to more and more dense material, the refraction will continue to move towards shallower and shallower angles, and that creates, in the long run, a curved path for earthquake waves. So back to a cross-section of the Earth. You've seen this before also. This is from IRIS, and it's showing you the different wave paths and a seismograph, or actually a bunch of seismographs, measuring this particular earthquake at various places around the Earth. So the way that you look at this stacked seismograph pattern is by picking out any one location. So for example, this seismograph that is 90 degrees away from the earthquake epicenter, and at this particular location, the P wave arrives first, and then a PP wave, one that has bounced off the surface and returned as a P wave, and finally the third major arrival is an S wave. So the P waves are generally the first to arrive, especially in shorter distances from the earthquake. The S waves arrive later, and take a look at the difference between these two. The P wave and S waves have different travel times. The P wave is faster than the S wave in all conditions, and as a consequence, the difference between the P wave arrival time and the S wave arrival time is a function of how far this recording station is from the earthquake. It's one of the primary ways that scientists determine where an earthquake happened, They can look at the difference in arrival time and figure out how far away their particular seismic station was from an earthquake. There is another wave that is the first arrival, and look down here at the bottom, the PKP wave. There is an area in the Earth far away from the earthquake epicenter where the P wave has to travel through the core in order to get there. And so the PKP wave is the first wave to arrive at far distant earthquake recording stations. So, in summary, travel time of a wave through a solid medium is a function of its density. And since we know time and since we know distance, we can calculate density. And geophysicists use this to figure out what the interior of the Earth looks like and is made of.